right, welcome back. The second part of Chapter 9 is all about bonding theories. How do we describe these atoms really sticking together to make those covalent bonds? So the first half was all about the shape. We draw Lewis structures, we get the electron domain geometry, we get the molecular geometry. Now we're saying, well, why are they even together in the first place? How are they staying together? What's going on? So again, for these descriptions in this chapter, these are older descriptions. These are usually theories or models made when we didn't have as much information, when the math was a bit newer and things were still being figured out. These are not, I would not describe them as accurate ideas. They're not correct. But again, like VSEPR, while they're not correct, they do get us close to the right answer without having to think too hard about it. And they can still be useful in describing or predicting some behaviors of atoms. So while these aren't the most modern theory, the modern theory is molecular orbital theory, and well, we'll pay lip service to it in this chapter for the AP classes. For college classes watching this, well, we'll get a little bit more into it. But we are going to say, well, what can we get from these that still applies? All right, so for this first one, valence bond theory. The idea being the bond is from the overlap of valence orbitals. That's how the electrons are going to be shared, because we're going to overlap the area between the two orbitals where those electrons are hanging out. So for H2, for hydrogen, we say, okay, well, one hydrogen has the 1s, the other hydrogen has a 1s, and those two 1s orbitals are going to overlap. And so the electron from this one, well, it can overlap and go over here. And the electron from this hydrogen can overlap and go over there. And that overlap is going to keep those two hydrogen atoms together. And that overlap can still happen between, say, a hydrogen 1s and a chlorine 3p to make hydrogen chloride, because we know they have to interact. The 3p is the valence orbital there. For chlorine to chlorine, for Cl2, 3p can bond with 3p, and there's overlap there. So the overlap allows the sharing to happen, and it's because we have electrons still with opposite spins. So we say, oh, this hydrogen is up, this hydrogen is down. Okay, they can sort of connect together and become paired. All right. And so the idea is, well, how close can they get? Well, if they're too far apart, there's no overlap, so the energy isn't really changing. As they get closer and start to overlap, we get some energy savings here. The energy of that system is lowered, so that's more stable. Eventually, they reach an ideal distance where the overlap is best, and that's where the energy is at its lowest. If you tried to get them to overlap even more, well, then your nuclei are starting to bump into each other. You're going to have positive versus positive, and that's going to send the energy back up because that's not very stable. So we have some ideal distance in here of this is how close they're going to get. But it's just always that, as they say here, a balance between attractive and repulsive forces to get the most stable distance between them. Okay, so VSEPR, it predicts the shapes of molecules really well. It did. Well, how do we explain that with orbitals? If we're saying, oh, it's a 1s from hydrogen and a 2p from oxygen or a 3p from chlorine, how can we explain the shape of a molecule based on what orbital should be involved and what VSEPR tells us should be the bond angle and the bond distance and all that. So we're going to use water as an example here. If we draw it, it would say, oh, it's going to be bent. We did that in the last video. There's 4 things around the oxygen, so that's the tetrahedral shape, but only 2 of those things are bonds, so that's the bent shape. And so if we look at oxygen and its configuration, 1s2, 2s2, 2p4, it's going to want to use these empty 2p orbitals. There's 2 empty spots there to share some electrons. And so, well, p orbitals, we said in chapter 6, they're 90 degrees apart, right? We have the x, the y, and the z. So if 2p orbitals are being used, they should be 90 degrees apart from each other. But when we measure the bond angle in water, it's really 104.5. And the tetrahedral electron domain geometry would predict 109.5. So why is there this difference? And so the real reason is complicated and beyond the scope of either course, AP or college general chemistry, beyond the scope of these courses. So what we're going to present next is the made-up answer, the fake answer. But it's the fake answer that gets us pretty close to the right outcome without having to think too hard about it. So I'm going to tell you right now, these hybrid orbitals, I would call them a complete and total lie. But the description we can give using them gets us pretty close to the right answer, and so we're going to use them. Also because the AP test asks you about hybrid orbitals, so I'm going to teach you this anyway. All right, so hybrid orbitals. The theory, quote unquote, behind these is that atomic orbitals will mix together and they will form a hybrid orbital that are equal in energy to each other. So they're degenerate again. And so this process, we call it hybridization. And so the basic rule is however many orbitals we mix, we get that same number of hybrid orbitals out. So if we mix 2 orbitals together, we get 2 hybrid orbitals. If we mix 3 atomic orbitals, we get 3 hybrid orbitals. If we mix 4, we get 4. So that's how we're going to know that everything is staying equal. We're not creating orbitals out of nowhere. We just take 2 to make 2 different ones. We take 3, mix them together to make 3 hybrids. That's what's going on with hybridization. And so we look at this. Beryllium. Its configuration is 1s2, 2s2. But beryllium can make bonds. It often makes 2 covalent bonds in its compounds. I say, well, how is that possible? The 2s electrons are already paired. And so we can say, well, maybe we give it a little bit of energy and we bump one of those electrons up to the 2p. So now we have 2 unpaired electrons. Okay, we can make 2 bonds. But these electrons are not equal in energy. One of them's in the 2s, one of them's in the 2p. So those bonds should not be equivalent. But when we look at the compounds and look at them with X-ray crystallography and bond enthalpies and all that stuff, nope, those 2 bonds are equal. So how can we explain that? It doesn't work. This wouldn't work. So what we say is we take a 2s orbital. We take one of the 2p orbitals. We mix them together. We hybridize them to make what we call an sp orbital, which is partially s and partially p, and those 2 hybrid orbitals are equal in energy. Right? And so, if these 2 are equal in energy, well, that's why the bonds will be equal in energy. That's why the bonds will be equivalent. Notice here, these other 2 2p orbitals that we didn't do anything with, they're still 2p. This 1s that we didn't do anything with, it's still 1s. But the 2s and one of the 2p's, they've now mixed to make 2 equivalent sp orbitals. All right. So if we can look at those kind of visualizing, s is a spherical orbital. The p orbital that we grabbed has these 2 lobes pointing in different directions. And so when we mix them, we say, well, in one case, we'll add them together. In another case, we'll subtract them. And so that's why they go in different directions. One of them says, I'm mostly to the right. The other one says, I'm mostly to the left. And if you overlap them, as they show here superimposed, that means one orbital can bond to the left and one can bond to the right equivalently. And so that's how we can explain how, say, beryllium fluoride, BeF2, has a linear shape where both bonds are equidistant and equal in energy because these 2 hybrid orbitals are equal but just pointing in different directions. Okay? And so here we go. 1 point's left, 1 point's right, and they can overlap now with the electron from the fluoride orbital. And so here we go. A 2p from the fluorine, a 2p from this fluorine, and the sp, 2 different sp, one to the left, one to the right. All right? And so that's how we can get them. We can get a similar idea with trigonal planar. If we take the spherical 1s and some, it would be the 2s here, but then also take 2 different p orbitals, one pointing one way, one pointing 90 degrees. If we mix them and combine them in different forms, one would go to one corner of a triangle, one would go to another corner, one would go to the third corner. And so if we overlap them again, that's trigonal planar. They're pointing to the 3 different points of a triangle. Again, not what really happens, but it's a way of visualizing how this works out. And so all 3 of these, what we now call sp2 orbitals, are equivalent, we call it sp2 because we took an s orbital and we took two p orbitals. 1, 2. So this 2 up here is not how many electrons are in there. It's how many of the p orbitals are involved. And if we say, oh, sp2, well, that's 3 things. We get 3 hybrid orbitals. All right. If we have sp3, this is very common with carbon. You take the s and you take all 3 of the p orbitals. And when you do the various combinations, you say, oh, each one points to a different corner of a tetrahedron. Well, that's how we get our tetrahedral geometry. That's how we get everything being 109.5 degrees apart. And because we used an s and 3 different p orbitals, we call them sp3. And so we say, oh, there's 4 things total. We get 4 hybrid orbitals. All right, so that's how we're going to keep track. All right, so now if we go way back to the beginning of this, how did we get this with water? Why is water 104.5 instead of 90? What we say is the oxygen has 4 things around it. So we make them equivalent by saying oxygen is sp3 hybridized to make the 4 electron domains equivalent. Well, if they're sp3 hybridized, well, that means the angle should be closer to 109.5. And so that's how we get that. And then we just say, oh, well, these 2 non-bonding pairs, they're taking up a bit more space. Remember, that's from the VSEPR. So that's why it squeezes down a little bit. And so we get this angle between HOH of about 104.5 because that's coming from hybrid orbitals, not the 90 that would come from just purely p orbitals. All right. Now, what if we have more than 4 areas? What if we have the trigonal bipyramidal? What if we have the octahedral shape? A while back, and this was on the AP test, they would say, oh, use the d orbitals. Bring in a 5th orbital, so we'd call it sp3d. And if we needed 6 things for octahedral, sp3d2. But now they're saying, hey, when we do more computational work, it doesn't actually look like it would do that. So on old AP tests, sometimes they'd say, what's the hybridization? And you would answer sp3d. But nowadays we're saying, you know what, that's not really accurate, so let's not use that. Again, none of this is strictly accurate, so I hate these questions with a passion, but they still love to ask, what's the hybridization on this atom? So I got to teach you that stuff. So sp, sp2, and sp3, that still shows up. sp3d and sp3d2, not so much. All right, so again, how do we summarize all this to figure out what we need? You're going to still start with drawing your Lewis structure. You'll use VSEPR to say, well, what's my electron domain? What's that main geometry there? You'll then say, well, what hybrid orbitals, how many do I need to make that geometry? So if you just need 2 for linear, well, then you need sp. If you need 3 for trigonal planar, sp2. 3 orbitals. If you need 4 for tetrahedral, sp3. Right? And so here we go again in summary. sp for linear, sp2 for trigonal planar, sp3 for tetrahedral. The other thing to remember here, strictly speaking, you have that many hybrid orbitals. So if we mix an s and a p, we get 2 sp orbitals. For sp2, we have 3 of the sp2 orbitals. For sp3, we have 4 of those orbitals because we put 4 things in to begin with, so we must get 4 things out. All right. So then what about double bonds? What about triple bonds? How do we do this? So how does a double triple bond form? Well, it can't only using hybridized. We've got to add some other things in. So we say the orbitals that aren't being hybridized, the ones that aren't being mixed in, they have what we call sideways overlap. The better way is it's a pi bond because of the things we'll talk about in a future slide here. So we have 2 main types of bonds. We have sigma bonds and we have pi bonds. And this is whether you're using hybrid orbitals or not. These are the bond types that we're looking for. So a sigma bond, it's head-to-head overlap, so straight on. And what we really say to make it a sigma bond is that it has cylindrical symmetry about the internuclear axis. The heck does that mean? It means if we have our 2 atoms, so here's the center of one atom and here's the center of another atom. if we looked down that bond, so if our eye was over here on the right and we were looking straight left and lining up those two nuclei, well, see how these lobes, everything's symmetrical. We would see the same thing the entire way. That's the cylindrical symmetry. So because we would see the same thing the entire way, no matter which way we tilted our head, that's a sigma bond. Pi bonds, on the other hand, have this sideways overlap. One orbital is going up, the other orbital is going down. Same thing over here. One lobe is going up, one lobe is going down. So they bond sideways. Notice that it's going to be p orbitals that do this. So now when you look down that axis from one nucleus to the other, you say, hey, wait a minute. There's stuff on top. There's stuff on the bottom. There's nothing in between. Something is not symmetrical there, depending on which way I turn my head or if I look in the middle. That's how we get a pi bond. Strictly speaking, it's when there's one nodal plane. So you could draw a straight line, as they do here, or a straight plane going through the two lobes, top and bottom. That's a pi bond. There's other types of bonding, like delta bonds, where you can do two planes, like in a plus sign, and say, hey, I can fit that plus sign down that axis. We're not going to talk about that in this course. But so that's why I don't want to say, oh, there's just something different. It's, strictly speaking, just one plane that kind of cuts it in half. So here, right here, down this axis, we can cut it in half. We have the top half. We have the bottom half. All right. Well, when we make bonds, whether it's from hybrid orbitals or not, the single bond is always a sigma bond. So if they ask you a question, and they will, how many sigma bonds do you see? You count up how many single bonds, that's the number, right? Or at least that's the minimum number. For multiple bonds, the first bond is always sigma, and then the other bonds are pi. So here's a molecule of ethene. It's C2H4. And so say, okay, if we just bring our carbons together, the carbon-carbon single bond, that's a sigma, right? We can look straight down there and it's all symmetric. If we add in our CH bonds, where we have our 1s from the hydrogen joining in, well, those are also sigma, right? They're symmetrical, they're symmetrical, they're symmetrical, they're symmetrical. So that's 4 more sigma bonds. Great. But for the double bond, to complete the double bond for ethene, we're going to take this pi orbital from this carbon, and this p orbital from this carbon, and the sideways overlap. Well, that's going to be a pi bond because it's now not symmetrical cylindrically. I could draw a straight line, and as they do here, that's this gray plane. This gray plane cuts right through the middle of the pi bond, one half on top, one half on the bottom. So that's why it's pi. So if we say how many sigma bonds total? 1, 2, 3, 4, 5. And then how many pi bonds? Just the one. If we had something like acetylene, which is C2H2, again, we have a sigma bond between the two carbons, because that's our first bond between them. We'd also have sigma bonds between the CHs. So we have 3 sigma bonds total. 1, 2, 3. But now for the pi bonds, well, we have these p orbitals still. One of them is going to overlap top and bottom. One of them is going to overlap kind of into the board and out of the board. And so those two, the second bond and the third bond of the triple bond, they're going to be pi bonds. So whenever you're counting, you say every bond is a sigma bond automatically, and then the double bond adds in a pi. The triple bond adds in a second pi. So that's where we're going with that. That's how you count how many bonds you have. All right, the last thing we're going to look at is how do we talk about localized or delocalized electrons? The delocalized was when we were talking about resonance structures from the chapter 8 stuff. And so if there's only one spot for them to be, whether it's a sigma or a pi, we're saying, nope, that's the only place they can be, they're localized. But if we drew resonance, especially for our double bonds, those electrons are delocalized, and they can spread out in different spots. Well, hybridization doesn't really give us a great way for that. We can say, okay, yeah, these carbons are sp2. That means there's still one p orbital not used. And if we drew them as localized, they'd be like this. But no, we should really draw them as delocalized with resonance, so that this big smear of electron density top and bottom, kind of as a pi bond, but spread out. So like, well, what is that? Well, we don't have a great way of describing that other than saying it's delocalized, at least not with these hybrid orbitals and with valence bond theory. What we would want to use to do this correctly is molecular orbital theory. And so in the college course, I'll go a bit more into detail with this. In AP, they've taken it away, so good on you. This is something that we'll come back to, so I've actually cut out most slides here in the PowerPoint, so college people, again, sorry, make sure you show up to lecture. But we're just going to very, very briefly talk about this. We talk about molecular orbitals that are still talking about wave functions, about where is the electron most likely to be, but instead of just around an atom, now it's where is an electron most likely to be in a molecule. So molecular orbitals are still very much like atomic orbitals. It's still 2 electrons per orbital. They have to have opposite spin, so one up, one down. There is a definite energy level of that orbital, and we can still visualize them. We can still say, hey, where is the most likely region of space for these electrons to be? So that's honestly what this picture is more like. This picture for benzene is where is this electron likely to be if it's in certain molecular orbitals. All right. Now, what they're different from atomic is that they go for the entire molecule, not just a single atom, and it's not even just a single bond sometimes. Sometimes it covers a wide area of space in that molecule. Whenever you have 2 atomic orbitals bonding, overlapping, interacting, we get 2 molecular orbitals. One will be bonding, one will be what we call anti-bonding. So bonding orbitals, that's where it's constructive, right? If these are waves, think about physics class, if the 2 waves line up, they build together and give you a bigger wave. That's the bonding. If they're opposite, if one is wave up at the same time the other one's wave down, well, they cancel out and say, nope, no bonding there, it just doesn't happen. And so we're not going to worry about nodal planes there. Now, some things that MO theory can give us that we can't necessarily get from other forms of bonding theories, they tell us whether molecules should be diamagnetic or paramagnetic. So this, for AP people, even if we're not doing MO theory, we need to know these 2 terms. Diamagnetism is when every electron is paired, right? Every up has a down. These substances, they are not going to be magnetic. In fact, they're weakly repelled by a magnetic field. It's just a little bit higher in energy when you put them in a magnetic field. But paramagnetic is when one or more are unpaired. So sometimes you'll still get a question about an atom of will this atom be paramagnetic or diamagnetic? So you'll draw out the configuration and say, well, do I have unpaired electrons? If they're unpaired, paramagnetic. If everything's paired up, diamagnetic. Don't worry about this third question of is oxygen paramagnetic or diamagnetic. We're not going to do this MO diagram, at least not in AP. College students, there's a good thought question when we get to that stuff. It actually turns out that yes, it is, but we don't need to worry about why. All right, so that's going to be the end of Chapter 9 for this video. In college, we will be doing more stuff in lecture, especially on molecular orbital theory. For AP classes, make sure you're focusing on knowing where do these hybrid orbitals come from, what are my shapes called, what are my bond angles. We need to know that stuff. All right, have a wonderful day.